Welcome back to AI.Code.Cast, the segment of the deep dive where we try to dig into some of the trickier problems out there. Today we're looking at the invert binary tree problem. Have you run across this one?
Oh, absolutely. It's a pretty common one, especially in those tech interviews. It can really throw people off.
Yeah. You think you've got it, and then you realize you've missed an edge case or two. So before we dive into solutions, let's start with the basics. What does it actually mean to invert a binary tree?
So picture a binary tree, right? But then imagine holding a mirror up to it.
Oh, okay, I get it.
The inverted version is what you'd see in that mirror. Essentially, we're going to be swapping the left and right children of every single node.
So if a node had, let's say, a left child with the value 5 and a right child with the value 8.
After inverting, you'd have the 8 on the left and the 5 on the right. Exactly.
Interesting. And this swap, this flip, happens at every level of the tree.
Yep, from the root all the way down to the leaves. Every single node gets flipped.
Okay, I think I'm visualizing it now. So let's say someone throws this problem at me in an interview. My first instinct might be to just go through each node, swap the children, and, call it a day. Would that work?
Well, it would technically work, I guess, but it wouldn't be the most efficient way to do it.
Right. I figured there had to be a more clever way to do it. What would be a better approach then?
Well, recursion's a good place to start.
Yeah.
It's often a natural fit for these kinds of tree problems because the structure of the tree and the structure of a recursive function, well, they kind of mirror each other.
Okay, I can see that. But how would we actually apply recursion to solve this specific problem?
Think of it as like delegating the task of inverting down the tree. Each node is responsible for inverting its own little subtree.
Oh, I see. Like a chain of command, but for flipping a tree.
Exactly. So you start at the root, tell the left subtree to invert itself, tell the right subtree to invert itself, and when they're done, you just swap their positions.
That's a pretty cool way to think about it.
Mm.
But are there any things we need to be careful about when using recursion? Any potential pitfalls?
Yeah, definitely. The big one to watch out for is the depth of the tree. If the tree's really deep, especially if it's like unbalanced, you could run into a stack overflow error.
Ah, that makes sense. Recursion's great for smaller or balanced trees, but we might need another strategy for those really deep ones.
Yeah, exactly. It's always a trade-off. But before we move on to those other approaches, maybe we should walk through the steps of this recursive solution.
Yeah, let's do that.
All right, so let's pretend we have this function called invert tree. Takes the root of the tree as its input. The first thing we do, check if that root is null.
Right. Because if it is, there's nothing to invert. It's like our base case, our signal to stop the recursion.
Exactly. But if the root isn't null, then we make two recursive calls. One to invert tree with the left child as the input, and another to invert tree with the right child.
So we're essentially telling the left and right subtrees, hey, go invert yourselves, just like you were saying earlier.
That's it. And once those recursive calls return, we know that the left and right subtrees below that current node, well, they've been fully inverted, so now all we got to do is swap them.
Okay, so we take the left child, which is now pointing to an inverted left subtree, and the right child pointing to an inverted right subtree, and just switch their places.
You got it. Then, finally, we just return the root. It's now pointing to the whole inverted tree.
That's so neat. I love how recursion can take such a complex task and break it down into these simple, elegant steps. But you did mention earlier that we got to be mindful of those deep trees. Are there any other limitations or considerations for the recursive approach? So recursion gives us this really elegant way to invert a tree, especially when it's smaller or balanced. But I'm sure there are other approaches, right? What if we have a really deep tree and we're worried about those stack overflow errors?
Yeah, you're right. That's where iterative solutions come in handy. Instead of relying on that function call stack, we can manage the traversal ourselves using some other data structures like queues and stacks.
Okay, I'm intrigued. Let's start with queues. How can we use a queue to invert a binary tree?
So this approach, it's called breadth first search, BFS for short.
BFS, got it?
You can think of it like exploring a building, but you want to visit every room on one floor before moving up to the next.
Oh, okay. So instead of going deep down one branch like recursion does, BFS takes a more systematic, layered approach.
Exactly. And that's what makes it perfect for inverting a tree. We visit each node level by level, and as we do, we swap its children. Make sure we cover the whole tree in the right order.
Okay, I can see how that would ensure a correct inversion, but how do we actually implement it using a queue?
All right, so think of the queue like a line at a bank. First node in line is the first one to get processed. We'll start by adding the root node to our queue.
So the root's our first customer, so to speak. What happens next?
Next, we go into a loop. This loop keeps running as long as our queue isn't empty. And inside the loop, we dequeue a node. That just means we remove it from the front of the queue. This is the current node we'll be working with.
Processing those nodes one by one in the order they were added. Makes sense.
Now here's where we do the actual inverting. We swap the left and right children of that current node.
The same swap we did with recursion, right?
Exactly, but we're doing it level by level now. After the swap, we need to make sure the children of this node are added to our queue too. So we enqueue the left child and then the right child.
Adding those next generation of nodes to our queue. Got it.
And we just keep repeating that process. Dequeue a node, swap its children, and queue the children. The loop goes on until that queue is completely empty, which means we've visited and processed every single node in the tree.
Okay, I'm following you. It seems pretty systematic and avoids that Stack Overflow problem. What about efficiency, though? How does it stack up against the recursive solution?
Well, when it comes to time complexity, BFS is right there with recursion. Both visit each node once to perform the swap, so both have a time complexity of O(n), where n is the number of nodes.
So both are linear in terms of time. That's good. But I'm guessing space complexity is where things get a bit trickier.
You're catching on. So the space complexity of DFS really depends on the maximum number of nodes that our queue needs to hold at any given time. Worst case scenario is a really wide tree. That last level could have almost half of all the nodes in it.
Meaning our queue would need to hold a ton of nodes, so the space complexity could approach O(n) in that extreme case.
Exactly. But for more balanced trees, that queue is going to be much smaller. The space complexity for a balanced tree would be more like O log n, which is just the maximum number of nodes at the deepest level.
So the shape of the tree really matters when it comes to the space BFS needs.
Big time. This is where the trade-offs come in. BFS might use a bit more memory than other approaches, especially for those really wide trees, but it's a very robust solution. Really shines when you have those deep trees that could cause problems for recursion.
It seems like understanding these trade-offs is really important when choosing the right algorithm. Are there any other advantages or disadvantages of BFS that we should keep in mind?
One big advantage I like is that BFS is often easier to visualize and debug. You can walk through it level by level and really see how the tree is changing. And it's a super versatile algorithm. It can be applied to a bunch of other tree problems, like finding the shortest path between nodes or doing a level order traversal.
So learning BFS isn't just about inverting trees. It's a tool we can use for all sorts of things.
Exactly. It's a core algorithm in computer science.
So we've seen recursion, this elegant solution, and we've explored the systematic level-by-level approach of BFS using a queue. I'm ready for our final approach. What's next?
Next up is Iterative Depth-First Search, or DFS. This is where things get really interesting. So Iterative Depth-First Search, or DFS for short, it's kind of like, imagine a spelunker, right? Someone exploring a cave.
Okay, I'm picturing it.
Instead of checking each path at a level like BFS, they go deep, all the way down one path before backtracking to check the others.
So it's like the opposite of that systematic level-by-level approach we were talking about with BFS.
Yeah, exactly. And just like a spelunker uses ropes and markers so they don't get lost, we'll use a stack to keep track of where we've been in our traversal.
Okay, we talked about queues earlier.
Yeah.
How is a stack different?
Think of like a stack of books. You can only add a new book on top, and you can only take a book from the top. Last in, first out, you know.
So the last thing you put on the stack is the first thing that comes off. Got it. But how does this stack of books help us invert a tree?
All right, so we start by pushing the root node onto our stack. Then we have a loop that runs as long as that stack isn't empty. And inside the loop, we pop a node off the top of the stack. That's going to be the current node we work with.
So we're always dealing with the most recently added node first.
Right, okay.
That's starting to make sense.
Now here's where the inversion happens. We swap the left and right children of that current node, and to make sure we keep going depth first, we push the right child onto the stack first, if it exists, and then the left child.
Ah, I see. By pushing the right child first, we're making sure we explore the left subtree all the way down before we go back and look at the right subtree.
Exactly. And we keep doing that. Pop a node, swap the children, push the right child, then the left, until our stack is empty.
And when that stack's empty, we visited and swapped every single node, so we end up with a fully inverted tree.
Yep, that's it. Iterative DFS is really just mimicking what recursion does, but instead of relying on that function call stack, we're managing it ourselves.
This is fascinating.
Awesome.
So let's talk efficiency. Time complexity for iterative DFS. How does it compare to the other approaches we discussed?
It's the same ON, where n is how many nodes we have. We're only visiting each node once to swap the children.
Linear time complexity. I like it. What about space complexity, though? Does using a stack change things up?
Yeah, it does. Worst case, think about a skewed tree where each node only has a right child. Our stack would end up holding all the nodes in the tree.
So in the worst case, ON, space complexity, just like with BFS on a wide tree.
Right. But just like with BFS, the actual space we need depends on the tree's shape. For a balanced tree, our stack's maximum depth will be closer to the height of the tree, which is usually log n.
So best case scenario, with a balanced tree, we're looking at closer to O log n, space complexity. Much more efficient.
You got it. It all comes down to those trade-offs, balancing time, space, and the kind of data you're working with.
This has been amazing. We've covered 3 different ways to invert a binary tree: recursion, iterative BFS, and now iterative DFS. Each one has its own unique way of solving the problem.
It's been fun exploring these different approaches.
And to our listeners, thanks for joining us on this deep dive into the world of binary trees and algorithms. Keep those coding skills sharp, and we'll see you next time.